So in a previous video, I've looked at modeling the caustic of a parabola with light coming in obliquely, parallel rays of light coming in obliquely. And interestingly enough, there's a spiral symmetry about the caustic, which I'd like to investigate a little bit more by looking at the curve, both the parabola and the Tchirnhausen cubic as Bezier curves. Now, just to remind us about Bezier curves, the most familiar Bezier curve is the Bezier cubic. And to define that, this is used extensively in computer graphics. You define a Bezier cubic by a control polygon, it's a control quadrilateral, through 4 control points, A, B, C, and D. What I'm going to do is, I've just sketched them, but I'm going to specify the coordinates to be x0, y0, x1, y1, x2, y2, and x3, y3. I'm just accepting the defaults here. One characteristic of GXWeb is that by default, most parameters are locked. The exception is x, y, and t and theta, which are unlocked. But that means I can't drag d unless I unlock these guys. If I do that, I can then drag any of these points I want around. And I'd like to be able to drag them. Okay, so to create a Bezier curve, I need to create these lines, and the point E is going to be constrained using a proportional constraint. It's proportional t along that line. If t equals 0, E will be lying on top of A. If t equals 1, E will be lying on top of B. So I'm going to do the same with F, and I'm going to use the same proportion t. And the same with G, we use the same proportion t. So now, as I say, t is by default unlocked because it's used typically as a parameter. Now we can see those things go around, but I want one more line here, hi, and this is going to be constrained in the same way. H is parameter is proportion t along that line segment, and I is proportion t along that segment. And now if finally I put another point, proportion t along that line, again using the same constraint, now the locus of that point is my Bezier curve. Locus as t varies. There is my curve. I can see there's a couple of characteristics of the curve that I want to point out. One is that J at the hi is tangential to the curve at point J. And derived from that, because everything collapses up at the ends, point A is tangent to the curve. Line AB is tangent to the curve at A, and line CD is tangent to the curve at D. So we're going to use those properties. Now, as we move A, B, C, and D around, we can see how the curve can vary. Another thing you can do is you can put A on top of D and effectively get a cubic Bezier embedded in a triangle. And that is the way we're going to attempt to model our Tchirnhausen cubic. But first, let's do something else. We'll get rid of this. We're going to delete A, D, C. Sorry, what's going on? C, A, B, and D. So I'm going to delete all those 4. And we've now got a curve defined by 3 points, E, F, and G. I can, and this is, well, these guys are moving. I don't want them to move, so let me nail them down. X0, Y0, X1, Y1, X2, Y2, so that we've now got this thing stabilized. This is a quadratic Bezier. Now, quadratic Bezier still has the tangency properties, but it the curve it generates is a parametric quadratic, so X and Y are quadratic in T, and it turns out that means that it's a piece of a parabola. Now, if you're given a parabola, and you have 2 points on the parabola, then you can create the parabola, the piece of parabola between those 2 points, as a Bezier curve with control points, the 2 points on the curve, and the intersection of their tangents. So let's see how that would work with the problem we've been looking at with the curve y equals x squared. Let's create that curve first. There she is. The x squared in there. Now we've been specifically looking at the point at the curve between a couple of different points. The points where t is square root of 3 upon 2. And minus the square root of 3 upon 2. So now we need to create the Bezier for this thing. The Bezier, the control points, the third control point is going to the intersection of the 2 tangents into these points. So there's the 2 tangents. There's their intersection, and we can ask for the coordinates of C. Zero minus 3/4. Okay, so I'd like to turn this process upside down and start with those 3 points and build my parabola from Bezier, and then build the caustic, the Tchirnhausen cubic, from that. So let's start that process. Get rid of all that. Start again with my drawing. I'm going to put a point at. I'm going to put these 3 points in A, B, and C. I'm not going to put that on the axis because I'm going to give its coordinates. So don't want to artificially snap to the axis. The coordinates I'm going to give for it are what was it? 0 minus 3/4. I'm missing my parentheses. If I miss both parentheses cleanly, that's going to be fine. Well, it's sort of stuck that awfully close. These guys are going to need to come down a bit and in a bit, and we're going to need to zoom in. All right, that looks better. Let's give this coordinates. Get inside those parentheses there, or get rid of them all. Interesting. It's not what I want. Let's get inside the parentheses. Minus the square root of 3.2. Comma 3/4. And this one to minus the square root of 3.2. Comma 3/4. Okay, so there's my starting points. Because I'm not really interested in these numbers being visible all the time, I've nailed them down, so I'm going to hide them. And I'm going to create my Bezier curve in the way that we did a minute ago. We're going to make that proportion t along that line. Make this one proportion t along this line. And we're going to put a point, proportion t along this line. And take the locus of that point as t varies. So there's a little bit of curve. Let's check that it's the right curve to make sure we've done everything correctly. Let's look at the equation. Okay, minus x squared plus y equals 0, y equals x squared. That is the curve that we wanted, thankfully. So now, look, this is the point of tangency here. We don't really need to have the curve sitting there, but let me just make it grey here. And I'll make these guys grey while I'm at it. And I'll make this guy purple. Okay, so if I now take a line horizontal line through F, I'll make it horizontal, but make it perpendicular to the y-axis there. And if I take that and reflect it in the purple line, which is the tangent, then that line will envelop the caustic. We'll define the caustic basically as that is the reflected line. So let me have a look at the envelope of that as t varies. And so there we see the picture of the loop of the Tchirnhausen cubic when we get to the 3/2 location on our parabola. That's just got right to the tip, the crossover point. Okay, let me make that one grey as well. Shrink it if you like into the background. That is kind of our target. What I'd like to do is draw, can I create a control polygon for which that curve is the Bezier curve? Well, we actually know the location of that point. If you remember from the previous video, it turns out that point is at 0, 9/4. So let me put that in. Again, if I want to constrain the coordinates, I need to not have any other constraints present. So I'll do that and constrain it to a 0, 9/4. And let me just hide those two. And while I'm hiding things, I'm going to hide these two guys. We're going to be drawing a lot of lines. I want to get as many as possible out of the way before I start. Meanwhile, let me hide these constraints that also get in the way. Okay, cleaned up my drawing. So let me draw. So the control polygon is going to hit here. It's going to come down. It's got to be tangent to the curve. So there I'm eyeballing tangency. And let's sort of draw a control polygon that's kind of like this. And it's going to hit again there. It's going to be tangent at both sides. Well, I eyeballed the tangency, but we know actually something about the tangency. This curve is tangent when the light reflects at A and at B. We had worked out that the √3/2 place on this curve, on the parabola y equals x squared, is where that crossover point, the double point, lies. So this side of the control polygon has to pass through A, and we can do that using an incidence constraint, and this other side has to pass through B. We do that using an incidence constraint. And now this is clearly symmetric about the y-axis, as everything else in the diagram is. So therefore, it is a reasonable conclusion that the control polygon for the cubic curve here should be symmetric about the y-axis. So we can enforce that by making these two perpendicular. So we now have a control polygon that satisfies everything I can superficially get about this caustic curve, but I don't have any particular location for the baseline there. So I'm going to leave that where I can drag it, and I'm going to now construct the cubic Bezier defined by that curve. So let me do that. I'm going to put this point at parametric location S. Now let's just sort of pull it down here somewhere. I didn't want to do that, did I? That forced this out of the way. So let's not worry about that. Leave it there. I want this to be at location S, parametric location S, and this to be at parametric location S. What happened there is S is something which is going to stay fixed, and S was trying to stay fixed as I moved it, so it was pushing this end down. S and T behave somewhat differently in that respect. However, let me carry on with my I need to get rid of these axes. Continue on with my Bezier. This is going to be location S. This is going to be location S. Now, as we move S, I can't do it by dragging. I can do it from up here though, or I can free it up and then I can drag it. So let's do that. Now we can drag S around. As we move this thing round, this line here is tangential to the Bezier curve. So if we take the envelope of that line, that will give us the Bezier as S varies. And so there's my curve. Now that looks pretty good. It looks like it's a bit too big though. And I suspect that if I just pull this up, I might just be able to get it lying right on top. Let's zoom in on that, and we can see that the definition of right on top looks like it's when C lies on top of that, that line. Well, we can make that happen using an incidence constraint. Take C and pop it on top there. And now you can see it really does lie on top. If we want to not believe our eyes, and it's good not to believe our eyes, K0 is the, we can see is the parabola. Equation of K1 K1 is the K1 is the caustic. It's defined by the reflection, and then K2 K2 is this one that I've just created, which is the Bezier cubic, and we can see the two equations with K1 and K2 are the same. So what we've shown is that the caustic curve is, this loop can be defined as the Bezier curve with whose control polygon is equilateral triangle, whose center points of whose sides are these points A, B, and C, A and B lying at the root 3.2 location on y equals x squared, and C, the intersection of the tangents there. So that shows you how we can define the caustic in this case in terms of a Bezier curve. But interestingly, think of it, you can remove the curve out of this discussion and prove the whole thing involving lines, because the tangent to the original curve is just a line in the Bezier construction, and the tangent, the curve, the caustic curve, is just defined by a tangent line, which is also just a line in this Bezier construction. So we could phrase this whole thing as an elementary geometry question using only lines and no curves. And that's what I'm going to do next in the next video in this series.